first speaker after lunch is Nadia who will speak to us on modeling HIV/AIDS, preferential antiretroviral therapy, I assume that is, distribution in resource-constrained countries. Nadia.
Thank you. He just took 2 slides off my presentation. So I hope everyone enjoyed their lunch. As you said, I'm going to talk to you about modeling HIV and AIDS today. And I'm going to talk a little bit about my personal motivation to begin with. So as many of you have already heard, I spent part of my last summer in Uganda working with the AIDS Support Organization. We worked a lot with people who were being treated for HIV and people who were going to be treated for HIV. And so I was really motivated to look at it from a mathematical perspective. And so this is what motivates the rest of my talk. Thank you. So a little bit of background and definitions. HIV stands for the human immunodeficiency virus, and AIDS stands for acquired immune deficiency syndrome. HIV can be acquired through 3 main methods. So you can get it through the exchange of sexual fluids, through blood exchange, or from mother-to-child transmission through breast milk or in utero. HIV basically is a disease, very generally, that attacks the immune system and prevents your body from being able to fight off outside infection. And once the disease progresses, the person can develop AIDS, in which the immune system is basically has failed and cannot protect itself from outside infection, and this leads to death eventually. HIV is one of the largest health problems that we're currently facing in the world. 33.2 million people are estimated to have had HIV or were having HIV in 2007. And on this plot, the darker red signifies places where the prevalence is over 15%. And when I speak about prevalence, which I'll talk about a little bit later, is the proportion of the population that is infected with HIV. So you can notice that in a lot of sub-Saharan African countries, we have these darker red shades, and specifically in the countries in southern Africa, we have populations where 15% or more are infected with HIV. And so this just goes to show that this is actually a health problem that we should be worried about and aware of. HIV can be treated, and the treatment is called antiretroviral therapy, or as I'll refer to it from now on as ART. It's an effective lifelong treatment. It's been found to extend people's lives who have HIV. But it is a daily medication, and it does have to be taken every single day for the rest of the person's life. The virus is a very smart virus, so if the person does not take medication every day, it can actually become, the virus actually becomes drug resistant, and so the medication is actually ineffective. The drugs are very expensive, so $300 to $1,200 a year, and this is sort of like the warehouse wholesale cost of these drugs. So you can imagine that a lot of the people that are infected with HIV that we saw in the previous plot are living in developing countries where this is just a ridiculous amount of money to be paying for medication and drugs. So it poses a problem of how are the people who need medication going to get medication if they can't afford it. And governments don't have enough medication to give to all the people that need it. So the World Health Organization recognized that this was an issue, and they produced this document that recommended fair and equal strategies for ART distribution. So they were really concerned with the ethical side of treatment distribution in resource-constrained countries. So all the highlighted words are either fair or equitable or equal and things like that. And one of the recommendations that I'm going to focus on for the majority of the talk is identifying vulnerable and marginalized populations that might not normally receive treatment, but the recommendation is to focus on these populations and try to give them more treatment. So the 2 subpopulations I'm going to focus on are women and rural populations. Now what the World Health Organization is trying to do is a very noble task. They're trying to make treatment distribution fair and equitable, but as a mathematician, I might not necessarily be concerned with being fair and equitable. I might be more concerned with what is this doing long term. So how is the treatment distribution they're recommending going to affect HIV in the long run? So that's exactly the question that I'm asking for my thesis. Are the World Health Organization's recommendations for fair treatment allocation going to lead to effective disease control? And the way we're going to do this is develop a mathematical model which we can examine preferential ART treatment with. And the 2 subpopulations, again, that I'm going to be looking at are women and those living in rural areas. And I'm going to look at combinations of those as well. The ultimate goal of this project country of Uganda, specifically because I went there this past summer and had personal interest in the matter. So those are the basic outline of the thesis and pretty much what the talk is going to go like from here on out. My accomplishments were that I developed two models. One was a preliminary model and one was an advanced model. I was able to perform a sensitivity analysis on both of those models, basically to determine what parameter ranges were the most stable. I found and tested the basic reproductive number, which I'll talk about in a little bit, so don't fear if you don't know what that means. And I completed dynamical systems analysis for the preliminary model. The final thing I'll talk to you about today is the treatment simulations that I ran and the conclusions that I could draw from those treatment simulations. The things that I'll talk to you about today are highlighted in red. I don't have time to go into the details of all of them, but if you do have questions on the sensitivity analysis or the dynamical systems analysis, I'd be happy to answer them later. So here is the structure of the preliminary model, and this is a compartment diagram for those of you who might not be familiar with this. The S stands for susceptible individuals, those who do not have the disease, and the I stand for infected individuals, those who do have HIV. And again, this is a very preliminary, simple model. The dotted line represents interactions that are leading to HIV infection. So when I talk about interactions, I'm saying that a susceptible male can interact with an infected female. Pink is female, blue is male in this case. So a susceptible male can interact with an infected female and become infected. So the dark arrows are the progression arrows. It's a very simple model, but you'll note that I'm only taking into consideration one mode of transmission that I mentioned before. So one of the primary assumptions of this model is that only heterosexual transmission is happening here. We're not seeing any mother-to-child transmission, and we're not seeing any transmission through blood exchange. So it's a very big assumption, and I recognize that, but that's what I decided to do for my model. So although this is pretty interesting, when it comes to compartment models, this is actually rather simplistic. So we're going to look at a more complicated, my full model structure. So before you freak out, the green oval represents the first population, and the orange oval represents the second population. Now you can imagine the green population is from a very urban area, like Kampala, which is the capital of Uganda, and the orange population is from a very rural area. So again, we have females and males, but our interactions are now coupled. So a female in the first population can be infected by a male in the first population or by a male in the second population. So we have a lot more interactions that are going on and taking place. And you'll notice that besides adding a second population, we've also added two compartments. The first compartment is the AIDS compartment, people who have AIDS. The second compartment is the treatment compartment, so those who are being treated. You'll notice a few more assumptions are being played here. The AIDS people who have AIDS are not interacting with anybody. So one of our main assumptions is that those who have AIDS are actually too sick to infect anyone else. And another assumption we're making here is that treated individuals have been educated on how to protect themselves and to prevent the spread of the disease, so they're also not infecting others. So the assumption about AIDS individuals being too sick has actually been verified in the literature. The second about the treatment might not be so verified, but we're going to assume that for the time being. So I'm about to put equations on the board as a warning, and this model has 16 nonlinear differential equations. I'm only going to show you 4, and those